Hello, and I would like to record a video here which demonstrates to you the intuition behind charging a capacitor and discharging a capacitor through a resistor. That is to say, most circuits that we have where we charge a capacitor and then discharge a capacitor are going to be circuits that don't have zero resistance. So even when we've examined charging a capacitor before, we've been assuming that there is some resistance that we usually neglect in the circuit. So we should now take a look at the details of what we call an RC circuit. RC stands for resistor and capacitor, both in the same circuit, and all of these circuits will be DC, that is direct current circuits alone. So what I have here in this simulation is I have a battery and I have set it to 1 volt. I can change the voltage here along the slider. And what I have done is I have charged this capacitor. So for now, we're not going to be looking at the details of how the capacitor was charged. Let's just imagine that the capacitor was charged. And in fact, the capacitor itself was charged to 1 volt. Notice that we're showing here the capacitance of this capacitor given the separation between the plates. Let's assume this is a parallel plate capacitor with square plates. And let's assume we can set the area, but the area has been set. That sets the capacitance as well. And we're showing the charge and we're showing the stored energy. Over here, I'm also going to show the charges between the plates, bar graphs, electric field, and so on. Now what we're going to do is, this now is the neutral position of the wires. This is a capacitor that is separate from the battery. It's isolated, so to say. And we're going to move the wires over to position B. And position B is going to be the position where we can discharge the capacitor through this light bulb. So let's see what happens. Notice that there's a discharge of the charge in the capacitor through this light bulb. You'll also notice a direction of the electric current. Let's see how we can charge the capacitor again. Notice that when the capacitor is charging, you'll see for a very short time, that's because the resistance is very, very small. Let's assume the only resistance we have is some sort of maybe internal resistance in the battery, if it's not an ideal battery. So notice that the electric current goes in this direction, which is, let's see, counterclockwise, and that's because negative charges are coming off the positive plate and are moving over here to the negative plate. Notice the electric field is from positive towards negative, and thus the capacitor is now charged. Now when we discharge through the light bulb, you'll notice the light bulb is very bright at first and then in some sense asymptotes down in its brightness. You'll see that there's a lot of charge that discharges at first and then more slowly, but indeed the charge is still dissipating with time. So watch one more time here. Notice that there's a very rapid discharge of charge at first and then slower and slower, almost as if there's an exponential decay. And in fact, that is what's happening. Notice also the negative charges move counterclockwise in this circuit because they're moving from the negative plate of the capacitor to the positive plate of the capacitor, whereas they moved from the positive plate over to the negative plate when we charged it. So notice that even though they're both counterclockwise, really the charges are going in the opposite direction, because instead of going from the positive plate to the negative plate to charge, they're going from the negative plate to the positive plate to discharge. And keep in mind, we discharge through the resistor, and that is to say we are changing the energy from charge into a different form of energy, namely light or heat. Let us now be a little more quantitative and a little more descriptive about how we charge a capacitor with a resistor and how we discharge a capacitor with a resistor. Now, in this first case, we're going to charge the capacitor, so a battery will be in play. Now, let's assume this is a EMF source that is an ideal battery. You notice the epsilon. And notice that all the resistance is in this resistor. Now keep in mind, this resistor could be including the internal resistance of the battery, because that would be in series with this resistor, and this resistor could also include an entire resistor network. In previous videos, I've discussed how to add resistors together in series and parallel. But for now, let's just call it a single resistor, because that's not the focus of this video, is to talk about resistor networks. So what we have is we have an EMF, a capacitor, and a resistor. Let's assume the wires are ideal. The resistor is set right now to 1.5 mega ohms. That's 1.5 times 10 to the 6th ohms, mega meaning million. And then we have 1.5 microfarads, so that's 1.5 times 10 to the minus 6th farads for the capacitance. We are going to plot the charge on the capacitor plates versus time, and the current, the electric current that's in the circuit, as a function of time. We'll do that after we close the switch. Now you should be able to try to predict what happens before this occurs. Think about what this graph should look like, and then we'll talk about it. Okay, so welcome back. I hope you had a chance to pause and think about what should happen. So I think at first, the capacitor should act like a piece of wire. Why is that? Because the idea is that the capacitor allows charge to go onto it very quickly because it's a conductor. When these are conducting plates that are empty of charge, there's an enormous rate of charge that flows from the positive plate to the negative plate. Now the positive plate will become the plate that faces the positive terminal of the battery, and the negative plate will be the part of the plate that faces or is connected to the negative terminal of the battery. Okay, so notice that the voltage will be unique on each of these pieces of wire, but notice that you can imagine there is a voltage drop across this capacitor and there is a voltage drop across this resistor. Now, we know that capacitance is charge divided by voltage, so voltage is charge divided by capacitance. So that's going to be the voltage change across this capacitor, and then the change of voltage across this resistor is going to be given by Ohm's law, namely current times resistance. Hopefully you can realize that the current is going to be very high at first, transferring charge, but then over time it's going to get less and less, because as we build up more charge on the capacitor, the charges, given that they have positive negative polarity, don't allow the current to flow as quickly. So the current, I think, should exponentially decay with time. Now the charge on the capacitor starts off at 0, and then it rapidly goes up. That's because the current is very high at first, but then over time we get more and more charge, but we should approach some sort of constant or some sort of maximum value. In fact, what we should approach would be a horizontal asymptote, and that would be the maximum charge of the capacitor, and the maximum charge of the capacitor should probably be given by C times delta V, and delta V is going to be the voltage of the EMF, because when the capacitor is charged, it's going to be maximally charged. Okay, so with that in mind, we should be able to charge this capacitor, and let's go ahead and close the switch. Notice that the current is now running. The conventional current is running clockwise in this case, from the positive terminal of the battery towards the negative terminal of the battery. Notice, let me just go ahead and reset this. Notice also after we close the switch, the charge goes up very rapidly on the capacitor. That's because the current is very high, but over time the current exponentially decays, and the charge on the capacitor approaches capacitance times the voltage, that is the EMF of the battery. And notice that that's going to be the asymptote, that's going to be the maximum charge. Notice that this is what we call a RC circuit during charging. That is, when we close the switch, we allow the capacitor to be charged through this resistor. Now, by the way, typically this resistor is going to allow charge to be stored at a certain rate that we're interested in. So we could change the resistance, but for now, we're just going to charge the capacitor through the resistor. So the resistor helps to modulate how quickly charge is stored on this capacitor. Okay, so next thing, we can go ahead and change the capacitance or the resistance. Let's reset, okay? And notice that, suppose the capacitance is larger. You should think about the time it takes to charge this capacitor. Okay, welcome back. Hopefully you did, and hopefully you think it should take longer. It should be a greater time. And indeed, that should be the case. It's a greater container of charge. In other words, C times epsilon should be a larger charge. So since it's going to be more charge because it has a greater capacitance, it should take longer to charge. So let's close the switch. Notice that we just moved this vertical axis value, this horizontal asymptote up. And so it definitely does take longer to charge this capacitor. Okay? And it also takes longer now for the current to decay. All right? So that's what we mean by charging a capacitor. By the way, this charge versus time graph is called logistic growth. Maybe you've seen this before, where it's a very rapid increase, but it asymptotes. And this logistic growth is given by a negatively decaying exponential function added to a constant value. And that constant value is that asymptote that we approach. Notice this indeed is exponential decay. So this is something like I max or I0 times E, and when I say E, I mean Euler's number. I mean the natural exponential raised to a negative power that depends upon time. I'll come back to this tau here in just a moment. Now, one more experiment. What if we were to increase the resistance? Well, if you increase the resistance, I think the current is slower to charge the capacitor. So indeed, it takes even more time to charge this capacitor. So let's go ahead and close the switch. And notice the current value, that is the C epsilon, is the same. But also notice that this I0 starts off smaller. Why is that? Well, that's based on Ohm's law. Notice that Ohm's law says if this capacitor starts like a piece of wire, epsilon divided by R, the maximum current, is less than when we started, but it definitely even takes longer because we cannot change the current as quickly having a larger resistance. So, notice that the time it takes to charge a capacitor will increase as the capacitance and the resistance increases. In fact, this thing we often call tau, this tau is what we call the time constant. The time constant of an RC circuit, also sometimes called the E-folding time, also sometimes called the characteristic time, is exactly equal to R times C, namely resistance times capacitance. The resistance is in ohms, the capacitance is in farads. It turns out if you work out the units, ohms times farads is actually seconds, believe it or not. So that's how it turns out. Okay, hope this makes sense to you, how we would use our intuition to understand what charge as a function of time and current as a function of time when we charge a capacitor would look like. And by the way, if you stay tuned for my other videos where I go into the notes, I'll show the mathematical equation for this. So I'll show the logistic equation for this and the exponential decay equation for this one. One more thing I should say about exponential growth or decay, namely this logistic growth or exponential decay, is notice that what is 0.632 here corresponding to this tau time? 0.632 is the same thing to 3 decimal places as 1 minus 1 over E. When I'm talking about E, I'm talking about Euler's number, namely that number you know to be about 2.71 to 2 decimal places approximately. And 1 minus 1 over E is the E folding time. In other words, this is the time it takes to get to 1 minus 1 over E, that decimal fraction, if you will, of the maximum value of the charge stored on the capacitor. Notice tau here also corresponds to 1 over E, namely 1 over 2.71, rounded to 3 decimal places, is about 0.368. That's the time it takes to perform one exponential decay in terms of 1 E folding time. Now, if you went out to 2 tau, so 2 tau, 2 characteristic times, would be 1 over E squared, E being the natural exponential. So hopefully you think about that this is a characteristic time of how the system tends to work. Now let us switch gears and let us have a look at discharging a RC circuit. Namely, how do we take charge off of a capacitor and discharge it through a resistor? Now, by the way, previously in the video I showed that was discharged through something like a light bulb. In fact, one very useful application of an RC circuit would be a flash circuit. A flash circuit is like, say, when a light bulb discharges, say when you're taking a flash photograph. When a capacitor discharges through that resistor, typically we want it to happen very quickly, so the resistance is very small, so that the time constant is very small. But that's what we expect to have happen in a flash circuit. Other examples you could imagine of an RC circuit where you discharge is like windshield wipers. When windshield wipers engage, during the wiping, there's a discharging of the capacitor, and then there's a certain amount of time where we charge the capacitor, and then we discharge. And again, you can set the resistance based upon the slider or the dial on most modern automobiles. Another example would be like a defibrillator. So you charge capacitor paddles and then you discharge, and the resistance has to do with the patient and then also the machine. But let's see if we can discharge this RC circuit. So in a moment I'm going to close the switch. By the way, also notice that this capacitor is set to 10 volts in this particular case. Also notice that we can set the capacitance and the resistance. One more thing is that there is no battery in this circuit. Since there's no battery in this circuit, I think the current should run in the opposite direction. It should run from the positive plate towards the negative plate. At least that's the direction of the conventional current. Again, we know that electrons are actually going from the negative to the positive plate. But with that said, we should say, okay, this differential equation, this mathematical equation should be easier to come up with. Why is that? Well, it's because that everything should just exponentially decay, I think. Because the charge should decay on the capacitor and the current should decay as it discharges through the resistor. So let's go ahead and see what this looks like. Notice that indeed it is exponential decay of the charge and it's exponential decay of the current. Notice in both of these graphs we reach 0.368. 0.368 at tau is again one characteristic time, which is called 1 E folding time, which is also called 1 time constant. And notice that's going to be the 3 decimal place value of 1 over E. So 1 over Euler's number, the natural exponential. So this is discharging a capacitor. Also notice that the maximum value of the charge on the capacitor was originally C times capital epsilon. And notice that that's exactly what the voltage of the battery was. And notice that the maximum current was I0. Now let's think about what happens if we increase the resistance. Well, if we increase the resistance, I think that there should be less current running at first. So it should take longer to discharge the capacitor. And that is indeed what happens. Okay? Notice that given that we have a larger resistance, we have larger current, we have smaller current by Ohm's law, because I equals V over R, V being voltage. So it takes longer to discharge the capacitor. And how about if we have greater capacitance? So there's more charge stored now on the capacitor, so this vertical axis value should be higher, and it should take even longer to discharge this capacitor. So with a small amount of current running and a large amount of charge to discharge, it takes longer to discharge the capacitor. Now again, in practice, there are variable capacitors in the world and there are variable resistors. I don't know what the exact name for a variable capacitor is. I think it just might be called variable capacitor. But a variable resistor is called a rheostat. And again, if you're going to, say, change how quickly the wipers, when it's raining, engages on a modern automobile, when you want the wipers to go faster, then you want the resistance to be less. If you want the wipers to go more intermittently, so have a larger time constant, you want to make the resistance larger. And that rheostat is what you're adjusting when you adjust the dial or the slider. Okay? So, thank you very much for your attention when looking at this video. This is RC Circuits. Please smash that like button if you like this content and subscribe to the channel to grow the channel. Please share this content with people that you know within your sphere of influence. And thank you for your supporting the channel, and thank you for watching. I will see you in the next video.